Welcome to day 2 of Machine Learning with Python workshop. There's some more information on workshop webpage on GitHub Wiki. Yesterday, we talked about some basics of machine learning, and we talked about some important packages in machine learning and data science in general in Python. One of them was NumPy for numerical arrays, and the other was matplotlib for visualization. And we talked about our, and we built our first classifier from Scikit-Learn, which was the decision tree. And today we will talk more about building, more about several types of classifiers. And we will start, and we will talk about some model validation. Model validation would be a way to assess the performance of your models. So we learn how to choose and use models from Scikit-Learn. And those, and one of the most widely used way of that would be cross-validation. So let's open Jupyter Notebook and load NumPy and matplotlib.pyplot subpackage. And there's one more package that will be used for today's workshop that is called Graviz. It is for visualizing graphs or networks, which is data structure consisting of nodes and edges connecting the nodes. Decision trees are are a class of graphs. So it will be used for visualizing decision trees. So it is not critical if you don't have this package on your computer, but if it is installed, you can see the graphs on your computer. If you're on Windows, we will use Anaconda prompt. Otherwise, you will open a terminal, then type conda install Python Graviz. You can also open terminal from Jupyter Lab interface as well, from File, New, Terminal. This is a command you would run. I have already installed the package, so I would not run this now. And this kind of command would be a simple way to install packages available from Anaconda repositories. And sometimes people will request you to use pip to install packages, and sometimes there will be tips on using conda to install packages. If both are available, the better way to go is often using the conda program, because that also comes with non-Python dependencies. In case of Graviz package in Python, it is interfaced to a Graviz software, which is not really dependent on Python. So if you are to install this package through pip, you will have to install the Graviz software separately. But if you install Python Graviz through conda, then it will ship with Graviz software. And if you go to the binder environment that I provided yesterday, it is already there. So if it takes too long for you to install this package, you can also go to binder. Let's load packages for today's workshop. NumPy as NP, matplotlib the pyplot as PLT. Those are commonly used idioms in Python to load those packages. And let's increase the font size in the figure a little bit. That is done by editing the RC params RC params attribute of the module PLT, where we modify the font size key to the value of 15. The data we will use today looks like this, simple but pretty useful. And if you look at this, your brain might immediately think that there would be two lines to construct decision boundaries, right? This line and this line, and upper left, red squares, lower right, red squares, upper right, blue dots, lower left, blue dots, right? Even if the solution is intuitive, there are some noises you can see. Red dots in this area, blue dots in this area. So it will be helpful to introduce many methods used in machine learning. You can download this data in our wiki or using the direct link provided here. And if you have already downloaded your materials, it is already there along with your .ipynb file. After downloading, move the file to the directory where your notebook is and unzip this if you are downloading this separately. You should have two files, call ML dataset, test dataset features.dat, and call ML test dataset labels.dat. On the tab left, you should be able to see those files. These two. And actually you can double click on them to see what's in there. It looks like a data file with two columns for the features and data with a single column for labels. They are zeros and ones. And you can load these text files to NumPy using the load.txt function. Call ML test dataset features.dat. We will name that features origin. And call ML test dataset labels.dat. We will name that labels origin. There's a command in Python to see the names of variables available. That is who. We have features origin, labels origin, NP for NumPy, and PLT for matplotlib.pyplot.
What's the meaning of this data set? Like those numbers? What do they mean?
They are locations on this two-dimensional space, basically. And labels represent red squares or blue dots. I forgot which one is red dots and which one is blue squares. Let's see. This one should be on the lower right part. Lower right part is labeled number 1. So yeah, red squares are labeled number 1 and blue dots are labeled number 0. Shapes of the features. Let's see. We had shape attribute for features origin array, which gives you a tuple for the size 500 by 2. So we have 500 rows and 2 columns for features. And for labels, it is a number array with 1 dimension, length 500. And to see unique values in an array, there is NumPy unique function. And you will see 0 and 1 if we run this, meaning that all the values in that array are either 0 or 1. And we can count how many zeros are there and how many non-zeros are there. NumPy has a function called count non-zero, counting the number of values that are non-zero. And running that on labels origin gives you 250. So we have 250 non-zeros and 250 zeros in that array. Another way to count zeros, we had Boolean comparison. What does this mean? What does this give? Labels origin equals 0. Can you tell me? Yep. How many values are equal to 0? So labels origin equals 0 gives you a Boolean array of truths and falses, whether each of the value in labels origin are 0 or not. And if you take sum on that by calling the sum method, that will count the number of zeros in that array. So that will also give you 250. And what we want to do here is to create a classifier that reproduces the labels in the NumPy array labels based on the features. And based on the shapes we have 2 features and 500 samples. But the common pipeline in machine learning is to do this. Before doing anything, it is a good practice to split out the data set into 2 subsets. One is training set, the other test set. Why are we doing this? To evaluate the performance of the algorithm after training a model objectively, we need to do that. We need to split the data into a training set and test set. Because what we want to see is the performance of the model on the data set not yet seen by our model. And we want our classifier to work well on the data points that our classifier have not seen yet. So the training set will be used to fit the machine learning model, and the test set will be used to evaluate the fit machine learning model. And test set should not be used in training in any way to see how well the model generalizes to the data yet to be seen by the classifier. So that will be our final proof of the model. We will use other methods not involving this test set to estimate accuracy during the creation of the model. Those methods include validation set, cross-validation, k-fold cross-validation, out-of-band accuracy, etc. So we will split this original data set into 2 parts. This part on the training set or the learning set is used to create a model, and we will only work with this data set in the training for training our model. And this part will be left out. This will be untouched until the very last moment. It is used to evaluate the performance of the model. And to have that step objective, the model should not have seen this part of the data in any way. Scikit-Learn has a function called train test split to help you split the data into 2 parts. And that is inside the model selection subpackage of train test split. And how to load that function would be this way: Scikit-Learn model selection. From that subpackage, we import the function train test split. And we pass the arrays to split as argument to this function: features origin and labels origin. And we also set the proportion of the test set 0.2 here. And the output, we will have 4 distinct arrays. Each array in the argument split into 2 parts. Features origin will be split into features and features test. Labels origin will split into labels and labels test. And we have the keyword argument shuffle here. If we put this to be true, we are shuffling the data and then split out the data. And if this is set false, we don't do shuffle, and the order of the data will be kept. And it is common to shuffle the data before splitting. And often we will not shuffle the data in this workshop, just to make sure that everybody has the same split.
Shuffle it, then how will we find what is like our training test data?
If you what?
Shuffle.
If you don't shuffle,
How does it determine?
that's just first 80% training set, last 20% test set. If we put test set to 0.2. If it is not shuffled, it is doing that. If we shuffle, then we shuffle the data set, and then first 80% is training, and the last 20% is test set. Yeah, not all data. Yeah, shuffling is often a good way, but for not for all scenarios. Actually, there are some scenarios where we should not shuffle the data. There often those would be time series data, the fluctuation of stock price, etc. Because for that kind of data, the ordering of the data is important. Then let's check the shapes of the output we have here. The shape of the features origin was 500 by 2. And for the training set, we have 400 by 2. The first 400 rows in the whole data set. And for the test set, we have 100 by 2. Last 100 rows in the original array they are. The first feature with index 0, we have this 0.07, 2.03. Labels for this would be 1.0. Does it make sense here? Yeah, it looks like it should be red squares. And we didn't shuffle because we didn't shuffle. So for the first row, we are getting 0.07, 2.0. We will train only on the features and labels array. The 80% of the data set, and we will leave the test set, features test and labels test for the future. We will not touch them. Oh, yeah, actually we are plotting label 0 as blue circles and label 1 as red squares in that figure up there. Let's start by visualizing this data set. And always what is recommended, even when visualizing the data set, is to only use training set. We don't want any bias to be introduced. How to visualize? We are plotting features with labels equal 0 for the verb, and we put column 0, feature 0 on the x-axis, and column 1, feature 1 to the y-axis of this figure. And for labels 0, we are putting blue circles. And labels 1, we are putting red squares. Then we get this figure. And we can, of course, add more details using what we learned yesterday. Maybe we can adjust the marker size, adjust the figure size to 4" by 3". We can also put labels on the x-axis and y-axis. Sorry. We run tight layout method to fit the figure to the frame. And to save the figure as a file, we give a file name and that's per inches for its resolution. And we're also showing the figure here with the plt.show function call. Then we will see synthetic dataset.png created on the left side. And you can see this PNG file created. Now let's train our decision tree on this. Decision tree classifier was inside the tree subpackage of Scikit-Learn. So the class decision tree classifier is loaded this way. And we will assign that to a variable CLF for classifier, short for classifier. And it will contain all the information learned by our classifier. To perform the learning step, we use the method fit. So clf.fit will be the way to fit our model. And the two arguments will be the features we will use for training and the labels we will use for training. Features expected to be 2-dimensional array, labels expected to be 1-dimensional array. So if we run this, we have our decision tree fit on the training data, features, and labels. And as I mentioned earlier, we have test sets, but you should never fit the model on the test set. Test sets are only for the final proof. To find the accuracy of this classifier, we can use the method score. So crf.score, and then the arguments will be the features and labels. And we get 1.0 out of it. Without any restriction, decision tree classifier can always make our model to perfectly classify all the data points. Unless there are some data points in exactly same coordinates. with different classes. So this means that our classifier was able to perfectly reproduce all the points. And we are not doing this to features test or labels test yet. We are still working on our model. The question to ask would be, are we overfitting or are we underfitting? And if a classifier is working perfectly like this, often we are overfitting. We can visualize the tree using the package Gravis. And this is a specific step we will take. We will export our learned tree to a file format that Gravis software understands. That is done by the export Gravis function inside the Scikit-Learn tree module. And Python interface for the Gravis software is what we import here, import Gravis. And we will define this function, show tree, taking a classifier as an argument. Then that will export the tree into the format that Gravis software understands. And from that Gravis format, we will visualize a tree. That is what this function does, Gravis.source.from file. And that file name is fixed as tmp.dat. If we run this, we will have our first decision tree visualized. Where is it? If you scroll down a bit, actually this is a huge one. So we were only seeing empty space there. Yeah, the whole view looks like this. What is the depth of this tree? 10 it is. The furthest distance from the root node on the top to the furthest down leaf node. And that looks like a lot of node. Considering what we visually saw from that plot up here. It feels like overfitting. So it looks so complex. But can we check this in quantitative way? Another clue to check it is seeing feature importance. In decision trees, splitting is performed according to a measure of dispersion of the data. By default, what it uses is Gini impurity. The more impure each part of the split is, the higher the impurity, and it is considered worse splitting. That Gini impurity is to be 0 when if both sides of the boundary has all the data in the same class. And if both classes are evenly mixed, it will have the highest value. And the goal is to minimize that Gini impurity. That is default for Scikit-Learn decision tree. And this enables the evaluation of an importance index. Gini impurity is used as an importance index for each feature that represents how much they contributed to the overall classification. So that weight based on Gini impurity can be computed using, can be retrieved using the attribute called feature importances. And we see 35% for feature number 0 and 65% for feature number 1. By the way, you can see that this attribute ends with an underscore. And what that means is that this is something that is determined only after the model is fit. That is Scikit-Learn's convention. If you try to access this kind of attributes before fitting the model, you will get an error. And you can see a list of attributes from the documentation page of decision tree. And you see those attributes ending with underscore available after fitting. Okay, where are we? All right. And looking at the plot, we know that the point -1, -1 should be of class 0, blue circles, and -1, 4 should belong to class number 1, red circles, red squares. And let's check if our classifier correctly classifies those points. That can be done by this. We will create an array with -1, -1, and -1, 4, and we will pass that to the predict method. Then we do get what we wanted. Class 0 for -1, -1, and class 1 for -1, 4. By the way, could you tell me why we use double square brackets up here? Anybody? The predict method always expects a two-dimensional array. So what we are doing here is passing a two-dimensional array with one row. That is defined by these double brackets. The outer square bracket would be would mean the entire array, and the inner square bracket would mean one row of array. And by putting this, we are defining two-dimensional array with one row and two columns. And for a model based on some probabilistic model, you can also check the probability that a given point belongs to a certain class using the predict probability method for a classifier. And we are not really presenting classifiers based on probabilistic models today. So it will always give you zeros and ones. But if you try this with classifier with some probabilistic models, such as linear discriminant analysis or logistic regression, then you would get some probability values there. Let's go to the break. We will return at 9:50, and after the break, we will talk about actually visualizing the decision boundaries. Which spot on the 2D array, 2D space are classified as red, or which spot are classified as blue? That is the question we will ask. Now let's visualize the decision boundary between classes. The boundary between the classes. The method we will use will involve NumPy and matplotlib, of course. Let's first try this. We learned a range yesterday, so we put a range from -2 to 5.001 with step size of 0.5. Then we will get -2 to 5 with step size increment of 0.5 for both x and y. And we can run this set of code to show the decision boundaries. Something like this. Let's break this down a little bit. What we are doing here, we are putting mesh grid there. And let's see what that does. The mesh grid function returns the coordinate matrices from the two coordinate vectors. If two vectors are given as its argument, it returns two-dimensional A by B arrays, each corresponding to x coordinates and y coordinates of A by B grid. So here is what happens. If we put nx equals 3 and ny equals 4, and we are splitting x coordinates into 3 pieces and y coordinates into 3 pieces, then what it gives you looks like this. X will be 0, 1/2, 1, and y would be 0, 1/3, 2/3, and 1. Then the result of mesh grid looks like this. If we put x grid with this x and this y, for x's, we get 0, 1/2, and 1 on each row. For the first returned value. And for the second returned value, we get 0, 1/3, 2/3, and 1 for each column. So we get this. And that is passed into Ravel function that just puts this into a one-dimensional array. That will be 0, 1/2, 1, 0, 1/2, 1, 0, 1/2, 1, 1, 2, 3, one more. And we do the same thing to the y coordinates. That will be 0, 0, 0, 1/3, 1/3, 1/3, 2/3, 2/3, 2/3, 1, 1, 1. And C underscore is somewhat unusual attribute of NumPy. This concatenates two arrays horizontally. So this will give you this array, each row containing coordinate for each of the points we want to make prediction on. And we pass this to the predict method, to the classifier. And before visualizing, we reshape that to the original size. That will be 4 by 3 again. And when we do Ctrl F, what we provide is an array of x coordinates, an array of y coordinates, an array of the same size containing zeros or ones. If we pass the numbers that way to the contour F function, we get the field contour plot. And with this color map named jet, we will get blue for class 0 and red for class 1. So variable function flattens the array. So if the what it passes this 1, 2, 3, 4, 5, 6, what you get is 1, 2, 3, 4, 5, 6 in a single one-dimensional array. And NP variable xv is this, NP variable yv is this, and concatenated result would be exactly this one. And delta is how fine the grid would be. With just increment of 0.5, it seems the grid seems to be too coarse. So this might not be a good representation of the decision boundaries. So let's decrease the value of delta to make the grid finer. How about 0.01? Then we get this decision boundary with our decision tree that we trained. What do you think? Do you think it is a good decision boundary for the data we have seen? Not really. It looks a bit too complex, right? So this can be considered a sign of overfitting. Maybe our model is allowed to be too complex. How do we restrict the freedom of our model and make our model simpler? Well, there is a keyword argument we talked about yesterday. We could control depth of the tree. So let's use some of the hyperparameters available in Scikit-Learn to modify the learning process. Max depth keyword argument limits the maximum depth of the tree. So we will just pass that restriction there and run our function. All others are kept the same. We fit using the training data, and we get the score to get accuracy. And we show the tree. The tree is much simpler than last time. And we get the accuracy of 82.25% with the training set. So it is lower than before. But what kind of decision boundary will we see? A much simpler one. Maybe a bit too simple. We don't know if it's better than the last one or not. We didn't discuss the quantitative way to compare them yet. How do you objectively find that out quantitatively? We will talk about that later today. But before going to that, we will talk about some more classifiers. Actually, literally more classifiers that is used together. Yep. This part. So this is a range starting at -2, ending at 5 with step size of delta. So it would be -2.0, -2.01, sorry, -2.0, -1.99, -1.98, and so on, going up to 5.00. Oh, this is just human chosen range based on the the location of the data points. Yeah, that is arbitrary, not done by machine.
So I guess for that, we just choose, it's just a very subjective choice, that we just put different numbers and then see how is the value, and then we see figures.
Yeah, that is what we are doing with these visualization. And we will get to objective way later on, a bit later today. So let's train more trees, and we can actually use multiple trees at the same time, and that is called random forests. This has been one of the most important models in machine learning before the days of deep learning came. And it still has nice thing because it is quick. It has been very important for applications that demands low latency. And random forests basically are an ensemble of decision trees. We train many trees and make a decision based on them using majority voting in most cases. Each tree trained with a subsample of the data set, sampled with replacement. So each tree is trained with a subsample of data set like this. We are randomly choosing 20% of the data set each time. Using this random number between 0 to 1, and we are choosing that only if that random value is greater than 0.8. And 3 examples of that will be this, and this. And on each of them, a separate tree will be trained, and those 3 will do majority voting to do final classification. That is done with the class called random forest classifier in Scikit-Learn that ensemble. And this kind of method is called bagging, short for bootstrap aggregation in the statistics world. Coding wise, it is pretty much same as what we did for decision trees. This is the documentation for random forest classifier. We will talk a bit more of it soon. And it is inside the ensemble sub package of random forest classifier. And we define our class, define our instance of this class by passing some of the arguments listed over here. We have n estimators. That is number of trees we train. We have max depth, maximum depth of each tree. OOB score, out of bag score. Do we have it? Oh, here it is. That is whether to use the out of bag samples to estimate the generalization score. That is something specific to decision random forest. And we will talk about that soon. And then we can fit our model on the features and obtain the out of bag score. Out of bag score of 94% we get. Out of bag score is score of each classifier in the ensemble by using the data points not considered for training that classifier. If 80% of the data are used for fitting a single decision tree, the remaining 20% are used to compute the out of bag score. And we are taking average over different trees. So that is one way of objectively computing accuracy of each tree using data not seen by our model. Yep. That is number of trees we are going to train, and that is still an arbitrary choice.
Like now you are going to choose 50.
Sorry?
But now you are going to choose.
How do you know I'm going to choose 50? Again, that is arbitrary choice, and we will talk about that later today. And let's see if this thing is any better than a single decision tree. Let's see the training score, 97.25%. Certainly better than decision tree limited to 5, limited to depth of 5. But not 100% compared to the case where we didn't limit the maximum depth of the tree. Feature importance, 49 to 51 split basically, which looks better in a sense because from the visualization of the data, it felt like each of the feature were roughly equally important when classifying these samples. And for the 2 points we used earlier, the prediction looks correct. Yes. That is based on that is also based on what we saw from the visualization of the data. It's because it roughly looks like that each feature is roughly equally important. So that is why if we see 70-30, we thought that might be a sign of overfitting. Still qualitative stuff. And quantitative way of determining that part has not been shown yet. We will get there soon today. And if you visualize the decision boundaries, doesn't it look better than the other things we have seen earlier? Boundary might be weakly, but in general, it's catching important characteristics of the decision boundary. Yeah, because random forests are ensembles of decision trees, we can access each tree we have trained, and we can inspect them closely if we want to. To do so, there's an estimators attribute of the model, and that will give you basically a collection of the trees you have learned. And to take the first one, we can take the one at index 0. And we can visualize each of the tree as well using the show tree function we have defined earlier. Another popular ensemble method, the method which was more important before the days of deep learning, it still works well in the cases that deep learning doesn't work well. For imaging and videos and natural language processing, there is where deep learning kills the field. But still, lots of parts in biology, there are places where AdaBoost works better when data are small and we don't have less features. So there still are places ensemble methods are very important and useful. One particular of them, and this one in particular is considered the best out of the box ensemble model, considering various data sets from several areas. That is called ADA boost. ADA boosting, short for adaptive boosting. The primary idea is to fit an initial tree and then add more trees, paying more attention to those samples that are misclassified on the earlier trees. So this is the idea of boosting. We start with original data and we train a classifier. Some will be correctly classified, some will not be correctly classified. We put more weights to the samples not correctly classified, and we put lower weights to the correctly classified data. Based on those weighted data, we train another classifier. There will be samples being correctly classified, there will be samples incorrectly classified. Again, we put higher weights to those incorrectly classified, lower weights to those correctly classified. We repeat this process to train many classifiers. And by taking weighted average of these classifiers, we get a really good classifier in total. This is how this ensemble is created. And it can be mathematically proven that it is okay for each classifier to be a weak learner, which means that they could be just slightly better than random guess. We will train many of them, tweaking so that those misclassified has higher weight. Then as a whole group, the resulting classifier can be a strong learner, a good classifier in general. There are many variants of this. There are things called gradient boosting, eta grad. Those are from the same class of classifiers. From Scikit-Learn example, we import eta boost classifier. That is the name of the class for this adaptive boosting. And as I said, each model, each classifier can be a weak learner. So it would work even with very simple models. Decision tree classifier with maximum depth of 2. The algorithm is something we can choose from. Oh, this is deprecated now. A set of choices. And number of trees we train is 200. If we run this, we get something perfectly classifying our samples in the training set. Let's see feature importances. 47 to 52, maybe okay. And it correctly predicts some 2 random points we have been using. And we can visualize our decision boundaries like this. In this case, it might seem a bit worse than what we have gotten with random forest. But in more complex cases, there are places where boosting works better. Particularly when the features are more human defined. For example, predicting cost of house, etc. Roughly speaking, it works better when there are few features and when those features are often and in getting those features, often human is being involved. Like in case of predicting price of the house, it could be like location of, it could be area, quality of life, crime rate, that kind of things. In that case, boosting relatively works better. It is less structured compared to the data where deep learning works better, I think. For images where we have a bunch of pixels, there deep learning works much better. And we don't exactly know why, but yeah, that is what is being observed. So far, we had common pattern in using Scikit-Learn. Most of models available in Scikit-Learn follow a very simple pattern. The model name will be the class name, and we define a classifier by passing some parameters to that class name or model name. This is step creating an object representing the model. And to fit the model, to train our model, we run the fit method with features and labels, features two-dimensional array, labels 1D array. Score, evaluate model's accuracy considering the samples provided. Features 2D array, labels 1D array. Predicts the class of the data provided, expecting features, which is 2D array. Yeah, it's better to say features here. Now let's talk about another class of classifiers. Support vector machines. It was for a long time the most widely used classifier in the machine learning community. Data are mapped to a point in a space, and we find a boundary so that the examples from different categories are separated by a clear gap, by a maximal margin as wide as possible in that space, and the mapping to high dimensional space. That is called the kernel function. And we have simple name for this, SVC for classifier, SVR for regression, support vector classifier, support vector regression. We are using this because it has pretty nice two parameters we can control for determining complexity of the model, C and gamma. C controls how much you want to avoid misclassification. Lower C, it is less sensitive to misclassification, resulting in simpler boundary. Higher C, more sensitive to misclassification, resulting in more complex boundary. Gamma controls how far each data point influences the points further away, resulting in simpler boundary. Higher gamma, gamma controls how far the influence of single string example reaches. Lower value of gamma, meaning it reaches far, resulting in simpler boundary. And higher gamma, meaning it reaches only the close range, resulting in more complex boundary. So they are two ways of controlling the complexity of the model. And that is in SVC class. And let's use default parameter for now. Just using default parameter gives you 96% training accuracy on the model. Let's try some different values of gamma and C here. How about high value of gamma? Then it lets you use very complex model, which can perfectly classify all the data points. Plotting the decision boundaries has been very repetitive, so let's wrap that in function now. It passes two arguments, classifier and delta, and it is basically what we have been doing for visualizing decision boundaries. A range to get X values and Y values, creating mesh grid of it, Ravu and C underscore to get a 2-column array, and we run prediction on them, and we draw contour plots, and decorating it a little bit with labels. That is what plot contours function will do. If we run this with the default parameters, this is the kind of boundary we get with support vector classifier. Looks really good compared to what we have gotten with decision trees. With high gamma of 10,000, it's all red except for those blue points. Might not be desirable, right? Let's lower the gamma, maybe what 10,000 is too high. C 1000 and gamma 100. It looks like this. Gamma is lower, so these blobs got a bit bigger. But we are trying to avoid misclassification or not as well, which is resulting in complex boundaries. Then how about looking at the value of lower gamma, but keeping C high? Then it results in complex boundaries in this way. We are no longer seeing these blobs, but does it look like a good boundary for the data we have? If we lower the value of C with the same gamma, we will get much simpler decision boundary. And we can try many different pairs of C and gamma. 0.5 and 70. 0.1, 70 looks pretty high. We still see these blobs a lot. C equals 0.1 and gamma equals 1. We are less avoiding misclassification. And gamma is rather low. So in this case, we get this kind of boundary. Looks good. 0.1, 0.1. Maybe oversimplified. C1, gamma 0.01. Maybe oversimplified again. But how do we objectively check which pair of parameters is the best? We will talk about that after this break. So, hyperparameters are the parameters that are defined when we created model, and those are what controls the complexity of the model. We had max depth for decision trees, and C and gamma for support vector machines. And what we didn't discuss yet is how we should objectively find the values of them. How do we choose them while avoiding underfitting and overfitting? Well, we have a bunch of data we have not seen in the training step yet. There's test set. Why don't we use that? You may be tempted to do so, but that introduces bias because that is still using test data in the training process, because selecting hyperparameters is part of training. So if you use test data for selecting hyperparameters, you are overfitting to the test data. Remember, we want our classifiers to generalize well to external data not seen by our classifier yet. So let's talk about systematic methods to tune hyperparameters without introducing bias. The simplest approach would be splitting the training set further into two pieces. We know that we should not optimize hyperparameter on the same data we use during training. So we split out one more piece of data, which is, and that part of data's goal is to fit solely for fitting hyperparameter. So we split the learning set, the set we have been working with, into two pieces again, training set and validation set. So now we have three sets, training set, validation set, and the test set. Training set is to fit the model. Validation set is to select the hyperparameters, and test set is to evaluate our final performance. And we should not mix validation set with a test set. We split the training set and validation set using the train test split function. And let's split out 33% of the set we have been using into validation set. And we will name the remaining part of it with suffix train, and we will put the validation set with the suffix valid. We are not shuffling again. Now the training set, we have 268 samples. Validation set, we have 132 samples. Test set, 100 samples. It's still there. Then the steps we take will be, for a set of hyperparameters, we will fit the model only using the training set, and we will compute the score on the validation set, not the data set not used when fitting the model. Then we will get some number for each values of set of hyperparameters. In this case, 51%, which is really bad. Maybe gamma is too high, or maybe C is too low. I guess gamma is too high. Now let's compare accuracy on the validation set to choose the value of gamma. So let's use this kind of grid. The next value is approximately roughly 3 times higher than the previous one, 0.003, 0.01, 0.03, 0.1, 0.3, 1, 3, 10, 30, 100, 300. And for now, let's fix C to be 1. And for each of the gamma, we are fitting the support vector classifier with a training set. And to accuracies list, we are appending the score on the validation set. And let's draw the curve of the set of gammas and accuracies on the validation sets. And this is what we get. X is on the log scale for gamma, and we have accuracy for each value of gamma. What we often see in this kind of training process is something like this. For lower value of gamma, we have lower accuracy. Why? With lower value of gamma, we might be oversimplifying the model. The model is too much restricted to describe the data well. We are underfitting. And if we have higher value of gamma, accuracy drops again. The reason in this case would be that we are overfitting. We are letting our model to be too complex in this case. And we want to find a nice balance between overfitting and underfitting. Try to find the value of gamma that maximizes the accuracy on the validation set. In this case, the value would be around 0.1. And because this training set validation split is performed at random, for better stability, to reduce the variance, we might want to repeat that splitting multiple times. How about 100 times? We are putting for loop here outside to repeat this for 100 times. And we are taking average over 100 trials. What do we see? A bit smoother. It has lower variance in general. Over 90% on the validation set. And we can look at the best performing value of gamma would be the fourth or fifth one. Fifth one in this case. And what is the fifth one? 0.3. Actually, you can do this part with your code as well, using the argmax function to get the index, giving the highest value in a numpy array. What would happen if you evaluate the performance on the training set? What do you think? Sorry? Be high? Accuracy will be high compared to what? As we do what? As we increase gamma? Yeah. Let's see. As you expected, as we increase gamma, training accuracy increases monotonically. But that is because we are letting the model to be more and more complex.
How do we know when it's over?
How do we know when it's overfitting? Yeah, that is when we are looking at the training set. If you look at the performance of the validation set, we see this. And now we can see we are overfitting.
I thought fitting accuracy should only go up. We'll just do-
Accuracy only go up only when we are checking the accuracy on the training set.
Oh, okay.
Validation set is the data set not seen while training. So yeah. So this is what the way we can objectively see we are overfitting.
This accuracy.
So this is accuracy on the validation set. This is accuracy on the training set. So on the training set, it will only increase.
Is there like a algorithm like they can take into account both these times, so the training data set and test data set, and then they determine the most optimal value for the
So that algorithm would be just from the bunch of candidates hyperparameters, you will fit the data on the training set and check the performance of the validation set, and you see this kind of curve. And you can find gamma that maximizes this validation accuracy. You in your code automatically.
Well, I mean, from this one, you still need to like subjectively choose the gamma.
Subjectively choose the candidate gamma value, or
You still need to. There are still some subjective factors.
yeah, that subjective choice is somewhat unavoidable for selecting the candidates for gammas.
So you're going to input more and more test data, like new test data, and then try again, and new test data, and try again.
New test data?
Yeah.
Yeah, often data will be limited.
Otherwise, you're biased because we are like adjusting the gamma value for this.
I'm not sure what you're talking about. So could you repeat?
So like when you see this kind of curve, you're going to adjust the gamma value again, and then introduce another layer of bias. So you want to like
Why are we introducing another level of bias?
because like you are now adjusting it based on the test data.
No, this is validation data.
Yeah. Oh,
Test data is untouched. It is still there. We haven't used it in any way yet.
okay.
This is validation data, okay?
Okay.
We split so we are splitting this set into two pieces, and we didn't touch test sets yet.
Okay, got it.
Does it make sense? So validation set will be the part of the data not seen in the training process yet, but it is separate from the test set we will use
Okay.
for the last stage. Yep.
Is there like a industry standard of how much we should separate into a validation set?
Industry standard.
You chose 33%.
Oh, yeah. Yeah, it is arbitrary and commonly used is often 25%, 33%. Between some kind of that. But yeah, industry standard, I'm not so sure about.
And also, so when you were initially setting the parameters,
Mhm.
You chose no for shuffling. Why does it matter if we shuffle before or after the split?
So if the data set were saying basically if the labels in data set was like 0, 0, 0, 0, 1, 1, 1, 1, then if we don't shuffle, it will be a trouble, right? If we don't shuffle, when the labels were like this, and we are taking less 20% as a test set, it will be a trouble, right? So standard thing to do would be shuffling.
Right.
Yes.
But we chose no.
Yeah, we chose no to that. Well, for teaching purposes, everyone to have the same data set.
Oh,
Yeah, that is why I was doing that. Does it make sense? Okay. So that is the simplest way of doing cross validation, splitting out validation set. And we randomly did that 100 times here to reduce the variance in the result. Having more complex models can reduce the bias, but the variance is high. Having simpler model introduces more bias, but reduces variance. So in statistics world, we call this kind of thing, this kind of curve we get would be coming from bias variance trade-off. That is the term used in that word. Optimize what? Yeah, you can fix the gamma to optimize C. And the most general thing to do would be build a grid of pairs of gammas and C's. And among those pairs, you could choose the highest performing one on the validated set. That would be the most standard way to do things. But as you have more and more hyperparameters, there will be more and more cases to try, so it will become much harder to check. So there are several set of methods in that case, such as Bayesian optimization or things like that. Now we have chosen best value of gamma to be 0.3, fixing value of C. That is the final. In this case, we are choosing gamma given the fixed value of C. And we have chosen gamma, and now we have the final step. Checking the score on the test set. Before that, we can do once more, compare what is average accuracy on the validation set between different values of gammas, just for checking purposes. But the final step would be training the model with the selected C and gamma and getting the score on the test set. So before checking the score on the test set, what we do is training the model on the entire learning set again. And then we fit our final model and then get the score on the test set. And this model with C equals 1 and gamma equals 0.3 gives you 95% test accuracy. Now, here's a bit more systematic approach on cross-validation, splitting the learning set into training set and validation set. And we randomly repeated that for 100 times. But there is a more efficient way called k-fold cross-validation. Here, we split the data, the learning set, into k pieces. In this case, k equals 4. And then for each round, we are selecting each piece of the training set as a validation set. For the first round, this part is validation and the remaining is training. For the second round, this is validation and the remaining 3 pieces are used for training. For the third round, this is validation, the remaining 3 are used as training. For the fourth round, this is validation and first 3 sets will be the training set. And then we select the hyperparameter on the average performance. And then we train the model on the entire learning set with the chosen parameters and check the performance on the test set. So we will choose the best performing hyperparameter on average with different validation sets. We have k-fold class in the model selection submodule. And for each fold of cross-validation, Scikit-Learn provides indices for the samples for training set and validation set. So we will define a kf variable with k equals 4 and splits equals 4. And we will have an object with k equals 4. And kf.split will give you an iterator that you can use in for loop, which provides the indexes for training set and indexes for the validation set. With this for loop, it repeats 4 times. Each time, it gives you the index for the training set and the index for the validation set. We choose training set using those indexes and validation set using those indexes as well. And then we train our model on the training set and get the score on the validation set. And over the 4 repetitions, we get 92%, 95, 96, and 98% on the validation set. And this there is a nice function that automatically does for you, of course, that is called cross-val score inside the model selection submodule of Scikit-Learn. Classifier will be SVC, C equals 1, gamma equals 0.5, and cross-val score for classifier will be this, CLF. And this will be the entire learning set, features, labels, and you will provide KF, the k-fold object, as an argument to this cross-val score function as well. We are using the same KF here, so we get the same four numbers, resulting from the cross-validation score, 92%, 95%, 96, and 98. So we can repeat this process with different values of C and gamma to get the C and gamma values that maximizes the average cross-validation score. And trying that with a different data set is set as homework. You can practice with some NumPy tricks to get the best performing hyperparameters. Okay. So on there's so on the lecture materials, there is day 2 exercise that IPY and B, and completing this worksheet will be your homework. For today's homework, you will work with Wisconsin data set, the data set we talked about yesterday as exercise 1. And you will repeat what we did in the class. You will split out the test data first and fit the decision tree using this data. And for a different set of candidates for maximum depth, you will choose hyperparameter max depth using 4-fold post-validation. And you check the final performance on the test set. We have a second data set provided in our repository, banana dataset. This is an array with 3 columns with 300 rows. You will read in the data and split out the test data first. And then this time you will fit the support vector classifier for this data. And consider a set of candidates for gamma and C, preferably a grid of values. And you will choose hyperparameters gamma and C using 4-fold post-validation. And you check the final performance with the test set. That will be your homework for this class. And as you know, homework is mandatory if you are taking this workshop for credits. Bioinfo 275 or Research Prep 199 or Research Prep 99. Deadline 10 days from the conclusion of the workshop, 2 Mondays from today. When is that? April 27th? 28th? 28th, is it Monday or Tuesday? 28th is Monday? Oh well, okay, then it is 28th.
How will I be evaluated?
How will it be evaluated? It will depend on workshop by workshop. But often, homeworks are graded pass or fail. If you submit your homework and if the instructor says it's satisfactory, you get full mark in that case. Often. And for quiz that is graded, you will get percentage for that. Does it make sense to you? If you want more details, you can ask Eloy about this part. Now, for the last part of the day, let's talk about evaluating performances of classifiers. To assess the performance of a classifier, what we did is comparing the classifier's predictions to the ground truth. Assuming binary classification, we will have 4 cases between classes 1, positive, and classes 0, negative. Ground truth, meaning the true label. And we have 4 possible combinations here, where ground truth is 1 and predictive class is 1, which is true positive. When ground truth is 0 and predictive class is 1, which is false positive. There are also cases where ground truth is 1 and predictive label is 0, which is false negative. And when ground truth is 0 and predictive label is also 0, that is true negative. And often what we have been using so far was accuracy, number of true positives and number of true negatives divided by all samples. And the score method usually computes accuracy for classifiers. But there is also a function called accuracy score as well. However, this is not always the best measure. In predicting if LA rains tomorrow or not, if you always say that it will not rain tomorrow, then you'll be correct for over 90%. But that is not really meaningful classifier, right? And there are many similar applications in medical and public health situation, particularly for cases where the prediction goal is check whether this person has a rare disease or not. In classification of malignant and benign cells, and if 1% of the cells are malignant, the accuracy of the classifier that always predicts a cell to be benign would be 99%. But that is not useful at all. So other measures are used for that kind of situation. Those measures would be precision, also called positive predictive value, and recall, also called sensitivity. So depending on application domain, those become also important. Precision is among those you predicted to be relevant, how many are actually relevant. So how many true positives are there among that are predicted to be positive? TP divided by TP plus FP. True positives divided by number of true positives plus number of false positives. And for recall, that is how many relevant elements did you catch among that are actually relevant? That will be number of true positives divided by number of true positives and number of false negatives. And there is a function for that in Scikit-Learn. We have precision score and recall score. Here's some visualization of it. So in the circle, is the sample predicted to be positive? Outside the circle are the samples not predicted to be positive. And on the left side of this figure would be the samples that actually are positive. And on the right side of this figure are samples that are not actually positive. And then we can find areas for true positives. Left side of the figure on the actually predicted to be positive. False negatives, actually relevant but not predicted to be positive. False positives, predicted to be positive but not relevant. True negatives, not relevant, predicted to be irrelevant. And precision is defined by this area among all predicted to be positive. And recall is this area among all actually relevant elements. So in some cases, precision is very important. In some cases, recall is very important. If making false positive is costly, then you will want precision to be high. If you don't want to miss people with rare diseases, then recall will be important. And there is a way to balance these two that is called F-score. And that is defined as harmonic mean of precision and recall. And more generally, you could put weight to either precision or recall, which is defined as F beta score. And putting the same weight to two of them will be called F1 score. And F beta score puts beta times more weight to recall than to precision. And this concept has been defined in 1979. So depending on your application, you may want to choose the most appropriate matrix when selecting which model to use. If true positives and true negatives have no big difference, then accuracy is okay. If missing a true positive is a great risk, F1 score is okay. And recall is also good. In medicine, precision, limiting the false positives, and F1 scores are widely used for analysis of prognosis performance. And they are all in Scikit-Learn metrics subpackage. Accuracy score, precision score, recall score, F1 score. And we can evaluate them on the test set for the final test. For example, some random forest classifier, we could get accuracy, precision, recall, and F1 score like this with 50 trees. And with the 4-vector classifier, we could do this to fit the model on Cn gamma and get accuracy, precision, recall, and F1 score. But yeah, this data we have been using, it was equally split between +0 and +1. So accuracy would be okay for this for this data set. But if you are in a situation to use F scores, precision, and recall, you can use these functions. And you can use F-score or precision or recall as a scoring metric for cross-validation as well. That is done by setting the scoring keyword argument to a certain value. In that case, if you are scoring based on F1 score and you are doing 4-fold cross-validation, you might run this kind of code to get the average performance on the validation set for the F1 score. Those F1 score is also takes a value between 0 to 1. So you will get this kind of result. And you will use the highest scoring set of hyperparameters to select C and gamma. There are other scorings available on this page as well. So today, we talked about some more types of classifiers. We talked about decision tree, random forest, and ADA boost, as well as support vector classifier. And we talked about the way to objectively select hyperparameters using cross-validation. Simple way would be splitting the dataset into 3 pieces, but the most efficient way would be k-fold cross-validation. Well, if you have resources to do that, the best would be having leave-on-out cross-validation, which is putting the k the same as the number of samples. But yeah, that is too much computation in most cases. So often we'll be happy with 4 or 5-fold cross-validations. And finally, we talked about precision and recall F1 score as a measure to be used when there is specific need, particularly in case of where the positives are pretty rare. And that is mainly about classification today. Tomorrow, we will discuss a bit about regression and some unsupervised learning as well. Thanks for coming and see you tomorrow. Oh, yeah, you do have a question? Scoring here? Yeah, scoring is just a measure to get a performance of a classifier or model in this case. And this scoring just means that we are using F1 score for scoring. Does it make sense to you? Any other questions? All right, thanks for coming and see you tomorrow for day 3.